Now I will continue with the same topic, pressure and fluid statics. I'm still in chapter 3 and still in this section. Actually, this is the last section. This is the section that I'm covering. I'm not going to the next section, 3-2. So all the things that I covered so far is in this section, 3-2. And now I want to discuss another example. Let us read this example with you. So a cylindrical container whose weight is 79 Newton is inverted and pressed into the water. So I have a container like this, okay, cylindrical container, which is, let me just change the color, which is this one. This is a cylindrical container. Actually, it is inverted, yani انقلب, and immersed and pressed into water. So you can think of this, sorry, let me change the color. So you can think of this as a container that contains, I don't know, so all of this is water, okay, all of this is full of water, as you can see. It is not shown. So I took this one, this cylindrical container, I inverted it, and I pressed it. So I applied a force here. So my hand is here, okay, so my hand is here. So I am applying a force on it to keep it in position. And the force that I am applying is F, okay. The weight of the container, the weight of this container itself, so the weight of the container itself is 79 Newton. The weight of the container, so I will just write here, weight is equal to 79 Newton. Determine the differential height h of the manometer and the force F needed to hold the container at the position shown. So the first thing, let me just erase this stuff here. I understood the problem now. So what I want this h here. I want this height, and also I want the force that are applicable to hold this container in position, so it's not going to move. So how to do this? How to solve this problem? As usual, you have to think of your assumptions, of your facts, whatever things that will help you to solve it. So I can say water is incompressible. I have water here. I have manometer fluid here, so these are incompressible. I can say that air pressure inside this tank is the same everywhere because the density of air is small. And then, as usual, we'll say 2 points at the same elevation will have the same pressure if the fluid is static and if they are connected by the same fluid. So by using this principle, I can start by, suppose now I want to find H, the first thing, this head here. So as I have just explained, so this water is just connected here. I mean, this is a tank like this, and this is the container in the tank. So I can say that, for example, the pressure at this point is equal to the pressure at this point, because these are 2 points connected by the same fluid and they have the same pressure. Okay. And then I can use another principle to say that the pressure at this point is equal to the pressure at this point. Why is that? Because, this is a container and the pressure everywhere is the same. Okay, the pressure everywhere is the same. So the pressure here is equal to the pressure here, and the pressure here is equal to the pressure here. So the pressure here is equal to the pressure here. But the pressure here can be easily calculated. I mean, the pressure here, so P, I don't know, let me call this point A. So PA is equal to rho GH. Rho is the density of water, 1000 kilogram per meter cube. G, you know it, 9.81 meter per second square. And H is given to you, 20 centimeter. So you can get the pressure at this point, which is the same as the pressure at this point. But once you know the pressure at this point, then you will say, now the pressure here is equal to the pressure here, because these are 2 points at the same elevation connected by the same static fluid. So if the pressure here is known, then you can say what? Then you can say that, for example, P is equal to rho GH. Okay, P is equal to rho GH. So once I know PA, so PA is equal to rho GH, but H here is this, my unknown, and rho now is the density of the manometer fluid, which is, density is equal to density of water times what? Specific gravity. So by doing this, you can solve for H. So this is the first part, straightforward. Let me erase all this stuff. So this is the first part, and you know how to solve it. The second part is also not difficult. Now he said he's asking for the force needed to hold the container at the position shown. So what is the force that I have to apply here so that this container will stay as it is? Here we have to use what is called force balance. So I am applying a force downwards, so F. What other force I have downwards? It says the force of the weight of the container itself. So plus W equals, what is the force that is trying to get things up? Okay, so this is the force which is coming from the pressure inside the container, and you know that P is equal to F over A. So F is equal to PA. So this is equal to PA. P is the pressure inside the tank, and A is the area, which is the area of the circle here. And you have the diameter, you can get the area of the circle. So F is my unknown. W, it is given to you, it is 79 Newton, equals, from where you will get P, you can get it. We have the pressure. We have the pressure here, which is the same as the pressure everywhere. We have calculated this from part 1. And A, you can calculate it. So this is known, so you can solve for F. Now, this is the solution. So I talked about the assumptions, and those are the properties. And then this is the density of the manometer fluid by multiplying the specific gravity times the density. And so this is the P air gauge, which is equal to this. This is the gauge pressure in the container, 1962 Pascal. And then we can use this to get H, which was part 1, and it was obtained to be 9.5 centimeters. So you can try doing this. The solution, I discussed the solution, and now it is in front of you with numbers. Now for part 2, as I said, you have what is called force balance, F plus W. This is the force that I am applying. This is the weight of the container. This is the pressure of the air inside the container, the gauge pressure. We're working with gauge pressure because atmospheric pressure is just working everywhere. And this is the area of the container. I solve for F. This is P air, which is, we got it from part 1. This is pi d squared over 4, which is the area of the container. And then we just rearrange it. So minus W, W is given to you. And we ended up with this force. So the force that I have to apply is equal to 59.7 newtons. Yeah, there is a discussion here. We could also solve this problem by considering the atmospheric pressure, but would obtain the same results since atmospheric pressure would cancel out. The atmospheric pressure is just applicable everywhere. It will cancel out. Usually, I will ask you to comment here on the force. So the force is 59.7 newtons. So this is like holding how many kilograms? Okay, so please comment. So please comment. Go back to maybe to chapter 1. Read the book. You know that each kilogram is like if you are holding 1 kilogram, how many newtons? So this is like holding how many kilograms. I will let this to you. Okay.